Imagine if this represented, and for all I know it does represent, some section of some molecule somewhere. And as you know, different atoms in molecules can either have slightly excess or a slight deficit of electrons near them, giving them a net positive or a net negative charge. For example, why do any two atoms stick together? Well, because you have these unfilled orbitals, right? And that tends, each atom tends to polarize the other, creating a dipole moment in the other one, and then they stick together. That's how chemical bonds work. And that's why the interatomic forces in molecules are due to separation of positive and negative charges. But it gets even more complicated with the quantum mechanics involved. But this is nevertheless possible. Now, what we'd like to do is talk about, when you have complicated arrangements of charges like this, we'd like a simple way to deal with the energy involved. So there's some key concepts here to realize when we start talking about energy and electric fields. Firstly, we already seen that if you have an electric field, whether it's due to a point charge or some other arrangement, it can put a force on a test charge, on a point charge. And if that charge can move, like if it's an electron or some other particle, or even a charged object like we saw here, if a charge can move in an electric field, then you have a force acting through a distance, right? And force times distance, you know from Physics 7a, is work. And work is energy. So there's definitely energy involved with electric fields, and we'll see with magnetic fields too. So if you want to move a point charge in an electric field, if you want to push it from one point to another, you're doing work to move it. Or it's doing work on you, right? If it's going in the direction it wants to due to the electric field, that's one thing. If you're pushing it against the electric field, you're doing work. So now we have to define what we mean by an electric potential energy. Obviously, if you have two positive charges at infinity, and then you bring them together to a certain distance, it takes work to do that. You're pushing against the electric. If you bring one in, you have to do work to bring it a certain distance in. And we call that electric potential energy. And it's just like gravitational potential energy. So we define something called electric potential, which you've already encountered in Physics 7b when you did the work with circuits. Electric potential is just the amount of work per unit charge to move a point charge in an electric field. Now, that might just sound like a bunch of words, but you already know that it takes work to move the charge in the field. Good. The amount of work per coulomb is what we define as electric potential. We could define the same thing for gravitation, but for gravitation it's just the acceleration of gravity. Acceleration due to gravity, because what do we do after all? Multiply it by the mass, right? So we could define a gravitational potential as, energy per unit mass. Now, just like with potential energy for gravity, we can set zero wherever we want. However, there is really kind of a preferred place to set zero. For example, when we have two charges, it's usually convenient to set zero when they're infinitely far apart. For systems like this, when we're dealing with electricity, we usually set the Earth to zero. The net charge of the whole world, the planet itself, is zero, even though charges are moving around. And this thing, for example, is directly connected to the ground. I think I've mentioned in the past that I'm a ham radio operator. I have an antenna on my roof, and not wanting my roof to antenna to get hit by lightning and set my house on fire, I made sure that my antenna was properly grounded. How did I do that? Well, one of the wires from the antenna, the whole radio system for that matter, is connected to a big rod, which I bought from Home Depot. You can go and you can find grounding rods. What is a grounding rod? It's about a 6-foot-long copper rod. And you take it and you pound it with a big hammer into the ground. That's exactly what I did. I made my own grounding system, made sure that it was really very well grounded. And then so the ground of my system, if lightning hits the antenna, all that charge goes into the earth and not into setting my house on fire, I hope. Okay, so that is a good place to call V equals 0, voltage equals 0. Electric potential is voltage. We measure it in units of volts. But we're going to need to do a little bit more calculation before we can define what we mean by a volt. And we're going to do it very precisely, though. So suppose we have a positive charge, a point charge, and it's fixed in space. That's Q1 here. All right, it's nailed down, can't move. And we have another charge, Q2, which is some particle or whatever, and it's a distance r0 away. And now we just let it go. Whoop, there it goes, accelerating off to infinity, being pushed away by the electric field. See that again? There it goes. Now we want to do that calculation. So we're going to start at r equals r0 and go to r equals infinity. We have to perform an integral. Sorry. But here it is. You need to see this once, I think. So let's see. If we have the force on Q2 is just its charge times the electric field at any point, at any distance r. So if that charge moves a tiny little bit dr, an infinitesimal amount dr, away, that's force through that distance. And that's an infinitesimal amount of work dw, which from our equations then is k q1 q2 over r squared dr. So all we need to do is integrate that from r naught to infinity to get the total amount of work to send Q2 off to infinity. If we do that, it's just an integral of dr over r squared, or minus 1 over r. Infinity gives 0, so you get just k times q1 times q2 over r naught. So you can say that the electric potential follows a 1 over r type law. So does gravity, for that matter, when you deal with two gravitational point masses. Well, that's slightly complicated. It's much easier to talk about voltage when we think about uniform fields. So how do we make a uniform field? Well, let's dip back into physics 7b and talk about capacitors. You remember, if you have a charged up metal plate, this one's positive, this one's negative, we can set this one to 0. We can connect it to ground, for that matter, even though it's still got negative charges on it lined up, and a line of positive charges here. That creates a uniform electric field in between the plates. And we like to do a little bit of calculation regarding that. So again, we represent our uniform field by a vector pointing to the left. So here's our electric field E. And now we bring in our test charge. And the test charge is going to go from the positive plate all the way to the negative plate. This is a much easier thing to calculate because the force is constant. Since the electric field is constant, the force is the same as it goes all the way. It still accelerates as it goes across and gains kinetic energy. But the work done by the electric field on the charge is the charge times the electric field times the distance. Force times distance. And that's equal to Q times the electric potential, V. V is the amount of energy per unit charge. And so we multiply it by charge to get energy. So if you just divide by Q on both sides, you see that the electric field then is V, the voltage difference between these two plates, divided by the distance. So it might be 100 volts and 1 centimeter, so 100 volts per centimeter. It would be a perfectly reasonable value for an electric field. But wait, didn't we say that our units of electric field were joules per coulomb? Way back when? Or newtons per coulomb, right? It's force per unit charge, right? It was electric field. Now we have new units for the electric field of volts per unit distance. So 1 Newton per coulomb, as a matter of fact, turns out to be 1 volt per meter. Now, if you don't remember anything else in this lecture about the units and stuff, remember this. 1 Newton per coulomb is 1 volt per meter, so I put it in giant type there. You can see that this is true pretty easily just by multiplying one side by coulombs and the other side multiply through by coulombs and meters, and you see that 1 Newton meter, which you know is 1 joule, is 1 coulomb volt. This is kind of our mechanical definition. This is where we connect are electric quantities to the mechanics stuff you did in Physics 7a and Physics 7b. So we can bring in all our favorite things to do with forces and acceleration and everything else from Physics 7a and b, but now we just add in the electric charge and electric field and electric potential. So this is the new thing to master. But I really want you to be well grounded in mechanics. No pun intended. Actually, pun intended. 1 Newton per Coulomb is 1 volt per meter. Now, another way to say this is that if you have a charge Q and it goes from one potential V to 0, let's say, as we did on the previous slide, it gains in kinetic energy Q times that potential difference, Q times delta V. That's pretty easy. So dealing with the energy things in electricity and magnetism is fairly easy because you just take the charge times the voltage and you get the energy. Now, we have kilograms, meters, seconds for human scale type things, right? We're going to quickly be dealing with things on the atomic scale, especially toward the end of the quarter as we get into the atomic physics stuff. And so we define an alternate unit of energy called the electron volt, which is simply then the charge on an electron times 1 volt. We see that energy is charge times voltage, so that makes sense. So let's just use the electron charge, because that's a typical atomic scale energy. So let's calculate what it is. How many joules is 1 electron volt? Remembering that 1 Newton meter is 1 joule, and that's 1 Coulomb volt. So go ahead and calculate that. You shouldn't need a calculator to do it.